Thank you, Sam. I'm Laura Neeson-de-Abruña, and I'm the new provost at MSU, and I'm very happy to be here. I wanted to explain a little bit of my interest in digital learning. I've been interested in that area of high-impact practices for at least 10 years at this point. In 2012, I started a Center for Digital Learning at Sacred Heart University in Connecticut, and offered workshops for the faculty in the summer and during the year. So I'd like to bring that tradition to MSU Denver. I've been here 2 months, so my first foray is to start this 4-part series on AI. I should also mention that I'm very interested in adaptive digital courseware. And if you don't know what that is, that's fine. I can explain it, I think, in a thumbnail. That is the use of AI sort of mixed with textbooks that are online that allow students to coach themselves through courses. We use it primarily in mathematics courses, but also in chemistry, physics, English, and engineering. So I have a driving interest in digital learning of all sorts, and I want to bring that to MSU Denver. I was really proud to meet Sam Jay because I think he's going to be the leader in all things AI. We've also just hired a director of online learning, Dr. Jo Jun, who will be with us on May 1st. She'll be part of the team as well as individuals in the Center for Teaching and Learning. So welcome to digital learning at MSU Denver. And now I'm going to hand it over to the maestro of AI, Samuel.
Thank you. Okay, everybody. So I don't want to burst any bubbles at the moment, but let's actually just start. Do me a favor. Complete that really quick. Survey. The goal of today is to really understand what is our conception of artificial intelligence. We have 2 wonderful computer science professors here who are going to take over the bulk of today's presentation, but it has come to the understanding of myself, and I think a lot of us who are using these tools, that we often use artificial intelligence as a briefcase term. We use it to explain automation, we use it to explain generative AI, we use it to explain machine learning. Machine learning, automation, these things have been around for a long time. What we're really talking about now, and really the impact that the access to ChatGPT 3.5 that came in November of last year has changed, is all of those AI-enabled resources like machine learning and automation are now possible for, I don't want to say the lay user, we have PhDs in computer science right here, but it makes it easier for somebody to take their data and to figure out, with the use of one of these tools as a partner, ways to evaluate, to assess, to project based on that data. And so, is everybody, we good? Let's see where we stand. Okay. Oh, the agenda, excuse me. All right, so there we go. There's the survey. So go ahead and complete that if you could. There we go. Maybe. Yep. There you go. It's not gonna, I'm gonna have to use it. I'll do it on my computer and put it up on the board. The questions are basically, I guess if you see it, how do you use how often are you using machine learning, generative AI, these kinds of things. We're ready for me to switch? All right. So as the provost had mentioned, we are taking what I believe to be a unique approach to how we're going to start using AI at MSU Denver. The goal is to provide you as university leaders with the basic understanding of artificial intelligence, so that way we as a community can start finding solutions to problems that could be made available by AI. We could do that at the department level, at the office level, and I really truly believe that there will be opportunities for us based on what we learn in these and we start experimenting with stuff to find opportunities to scale these resources
across the university and potentially even externally. Now, that doesn't mean that you're supposed to be some sort of engine for revenue, but it does mean that I guarantee there's somebody in this room who's going to learn something from today or the next 2 or 3 workshops, build something that could be applicable to everybody on this university's campus, which to me is pretty remarkable. And with that, sharing, but also opening up time to actually have conversation and to share and to experiment with these things. I know that's a really, really big idea, but I genuinely believe once we learn what is possible with this stuff, we're going to find ourselves with a lot more opportunities to think critically. I like the idea of having somebody who's potentially an entry-level worker, employee in student affairs, who has no background whatsoever in computer science, coming up with some sort of tool that changes the university forever. To me, that's pretty awesome. And right now, if you've seen some of those tools that are out there that are enabled by generative AI, it's very, very possible. Now, before we get into that, you got to eat your broccoli first, okay? So today, sorry to burst any bubbles, we are getting into the weeds a little bit about artificial intelligence. Reason being, we don't know what is going to happen with AI and generative AI moving forward. We know that computing power is getting more significant and it's not going to stop getting more powerful. And we know that the data that we are collecting, whether that's department level, committee level, organizational level, is not going to stop. We're going to continue grabbing this data. And knowing that, I think it's particularly important to understand what is AI at a very, very, very basic level. Because right now we're using ChatGPT or Copilot as our go-to resource for generative AI. But I need you to understand, or I hope that you will understand, 6 months from now, OpenAI may have a completely other tool, or Microsoft may have a totally different tool, a language model, if you will, that we turn to. And so it's important for us as faculty, staff, students, to have the thoughtful and critical awareness to be able to bounce back and forth across these different models, depending upon whether we need them to use to evaluate data, or to write syllabi, or to put together an MOU. It's really going to depend upon what works for you best in that moment. And so today we're going to really start with that basic understanding, because if anybody knows what this is, like music, you can't start writing a symphony until you give your kids some recorder they, make your life miserable with. Right? So with that, I now would like to present to you 2 of our fantastic computer science professors, Ranjita Rajad and Steve Gnites. They are, yes, Mark. I will write it up there. It's not working because it's not on my computer. Yes. Sorry, Mark. It was supposed to work. But no, I'm staying on the agenda. I'm staying on campus. And so what I've asked Ranjita and Steve to cover today for all of you is a basic kind of history of artificial intelligence, because it is important. And then it's going to come up to Steve, and then Steve's going to take over and get into the weeds a little bit about how machine learning has changed, how deep learning has changed, talk a little bit about neural networks and natural language processing, all that fun stuff, those buzzwords that we hear so often, we probably have no idea what the hell it means. Hopefully today you'll have a general understanding. And then at the end, there's a few more announcements I would like to make, and then including preparation for workshop 2, which will be diving deeper into generative AI, using or actually having some faculty and some staff who have been using those resources in order to share out. And so with that, Ranjita, the floor is yours.
Thank you, Sam, and hello, everybody. My name is Ranjita Rajan. I'm from Computer Science and an assistant here. So, I'm short, I know.
You just start talking. I'll figure it out.
Okay. Am I audible? So, if it, the screen is up.
No, it's not. Shoot. Of course.
Okay, I think it's good.
Okay.
Okay. Okay, it's me again. We'll start with the question. My role here is the recorder. So I will start with the history, evolution, and very basic level, and then I will head over to Steve. So we can start with a question here. Can you just guess the age of AI? At least those who are in the room. So whether the option is first, second, third, or fourth. So I'm going to walk you through the fourth option, that is more than 50 years. So AI is actually more than 50 years of age, and I'm going to walk you through from the dream to what we are today. We'll start with the birth of AI. It's in 1950. That is when my father was born. So we'll start with the question from Dr. Alan Turing. I hope you have seen this movie, The Imitation Game, which is mostly on how Alan Turing cracked the code to the Enigma. And there was a question after that particular event, so whether the machines can think. So that's the birth of AI. And for that, Turing proposed a Turing test, which you can see from the image. So if you have a screen and somebody is behind the screen, if you can say whether that's a human or a machine, then you pass the test. Otherwise, you fail the test. So from there, actually, we began the journey of AI. And many people work on those things and found what we have today. So next, after the birth, definitely it's a naming ceremony. So in 1956, there was a conference, that is Dartmouth Conference, where the artificial intelligence was named. Just like we seek for a good name for the conference, they also group and find a name for a conference from different names proposed, like cybernetics, automata theory. They found the best name, that is artificial intelligence. And McCarthy, Minsky, and Rochester, and Shannon is the father of information theory. So these amazing people grouped together to start with the summer AI research. And from there, they were researching on how this dream of how the machines can think can be made into the research and the reality. So after the naming ceremony, so we are moving to 1960s. It is the creation of perceptron. So when I say perceptron, we will see what it is. Actually created a neuron which mimics the human neuron. So as you know how our brain works, if something happens, then each neuron will be activated and the signals will be going to different other neurons so that we will do whatever we need, right? If you want to taste something, the taste neuron will be activated. So just like that, there was a one single neuron mimicked with the hardware. The first perceptron was actually built as a hardware, and then it was moved to the algorithm side. So the hardware works like this. So here you can see how you made the decision to be here or attend virtual workshop. So you can check for the weather. You can check whether the priority, whether I have under work, if I have a meeting with my provost, or do I have to attend the workshop. So definitely the priority comes, right? And then we will check if there is a virtual option. If you can drive or if you have some other engagements, you will see if there is a virtual option. And if you're deciding using these three features or parameters, you cannot give the same weight for everything. So I cannot give the weight for weather and my priority as the same one. If I'm giving the weightage of the priority as one and adding up it together and take the average and take the decision, it's not going to work because priority comes more than the weather, right? So weather can be sunny or it can be snow, but I can have a jacket or I can have an umbrella so that I can appear for the workshop, right? So here we are adding weights to the decisions so that the priority will have the high weight. So that I put the weights just some numbers based on me. So it can be different weight for different people. So if there's a virtual option, I have a weight of 3. For the priority, I have a weight of 5. And whether it's a low weight decision. So I can add these things together and consider a threshold and see whether the decision should be yes or no. So if I'm asking you, those who are sitting here, if these weights works for you, it may be or maybe not, right? Because for you, the weights may differ based on how you are coming into the workshop, right? So every time I can ask you and correct the weight so that I can get an optimized weight and the model will run for me. So that's the basic concept of neuron and how it's working. And definitely a single neuron will not give a good result. But here I put it so that we can see how it is working. And since the single neuron doesn't work, we have multiple layers of neurons so that we can have different features going as input into the model. And the model will correct the weight based on its learning, and it will give the classification result, whether the result should be yes or no, or you can classify between animals or birds or anything that is based on the data you have and the model that you have to train it. And again, these models are divided into different types. You might have heard about these names: supervised learning, unsupervised learning, and reinforcement learning. So supervised learning is we are labeling the data. So if you want to model a system so that it will identify cats, so you will train the model by giving the data or the pictures of the cat, and it will train by itself to classify whether the given picture is a cat or some other animal or something else. So that is supervised. We are labeling it and training the model so that it will identify whether it's a cat or dog, something like that. Unsupervised learn, we are seeing patterns. So anything that is related to cat will be grouped together. So here you can see 2 pictures, which is very similar. So the similar things will be grouped together and form a pattern, and we can get some insights from the patterns. And the third one is the reinforcement learning, just like we give treats to our pets. If some action is done correctly, then the weight will be added more into that, so that it will learn and identify the patterns correctly. So these are the 3 main different types. There are many other variations for this, but these are basically the 3 main types of learning in the machine learning side. And the most important part here is when we train these models with data, we must be very careful with the data that we are collecting and feeding into the model. There's one example here you can see, the Chihuahua and the Muppet. It's very hard to identify between these 2, right? So if we are creating a model for identifying a Chihuahua, then definitely we have to train with different kinds of data and see whether it's classifying properly. So that is very important because we have data now, but we have to see if it's good data which is going into the model and if the model is being trained with all the types of data. Going back to the timeline. So in 1960, the first perceptron was created, even though the first with the single layer was not a success. We are going forward to the next timeline. And in 1966, we have our grandparents born. That is Elisa, which is the grandparent of our Alexa, Siri, or the ChatGPT that we are hearing about. So Elisa was the first psychotherapist who can converse with the human. So how Elisa works is it's like a rule base. So if you are talking or conversing with Elisa and typing, "Today I am sad," then Elisa will identify the word sad, and there will be some rule-based thing working behind the scene so that it will say, "Oh, okay, are you sad? What happened today?" Some questions like that. So just a simple conversation. But in 1966, a conversation like this was huge. It was very fascinating to see how a machine is conversing with you when you are giving some inputs. Right? And then we have another grandparent here. Which is the grandparent of our self-driving cars or drones, we can say. It's the first machine, Shaki, which actually have all kinds of intelligent robotic system combined with AI, that is computer vision, and to see the things around the room and move around the room, motorized systems. So these are the grandparents of what we are seeing in today's world. So that was the birth and the initial side of AI. And then we had a winter in AI because of the low fund and the systems were not supporting, the perceptron was not giving the what is expected from a model. So there was a winter of AI from 74 to 90 with lower funds on not successful projects. And then after that, there was a boom with the expert systems. So when I say expert system, so here you can see the rule engines were supported by a knowledge base. So if you have some knowledge based on some area, then we can feed that into the rule engine so that it will take the knowledge and then give the recommendations. So the dental was the first recommendation system, which did the chemical analysis expert system, which was giving some analysis and saying which compound you have to use for some chemical analysis. So if you look into, I'm going a bit away from the history. So you might have seen the recommendation systems like that before. Because you have attended AI workshop 1, the recommendation is you can attend workshop 2, 3, and 4, right? Just like how the Netflix and Amazon Prime is recommending movies for you. So the recommendation system now is working for all areas like music or movies or anything. And even in our area where we have intelligent tutoring systems. So we can feed with the existing knowledge bases, and then we can have some good recommendation for the learner so that the learner will learn better. In 1980, we have the expert systems, and then we have the back propagation, which actually does the classification of images. So the picture that you are seeing here is classifying the handwritten zip code numbers. So those pictures can classified using the convolutional neural networks. So we will be saying more about the deep learning networks. I'm not going in depth of this, but here you can see the pixel is considered as features, and the features are learned based on how good the classifier is working. And then we can identify whether the number is 3 or 4 based on the classifications. And this is happening in 1989. And then again, there was a winter because the Lisp programming language, which was supporting the AI algorithms, were down market. And then we don't get the expected result from different expert systems. And the funding was not there. So there was a winter after the expert system and the back propagation. And then comes the short eye. In the Renaissance side, I have picked only very few, which is very important. So the first one is the chess competition with Gary Kasparov and the IBM Deep Blue, where IBM Deep Blue had the win. And that was when we realized that, okay, the machines can do so much than we anticipated. And that was a seismic shift from what we think about the machine and how it could act. And in 2010, we have the ImageNet, which was a huge competition for the neural networks. And with that competition, we have a huge amount of data came in so that it can train the neural network. So the data collection was huge after the ImageNet, and we have a huge database so that we can use that for the modeling side. Then going forward, we have the current thing that seeing now, the OpenAI, they grouped together to form. And I think in 2015, that was not a part of the history, but now it's a part of the history because now OpenAI has come a lot and we have the GPTs and the ChatGPT. So now it's a part of the history. So 2015 is a year where Sam and the team grouped to form the OpenAI. And in 2016, we have the DeepMind's AlphaGo, which the AlphaGo from the DeepMind actually compete with the world grandmaster for the Go game, which is an Asian game. And the difference between the chess and Go is the Go has the infinite movements, infinite number of movements, near infinity, and the complexity was very high. And AlphaGo could win the then Grandmaster Lee. So it was a huge win for the machine as using artificial intelligence. So these were the short times, and now we are moving to what we are seeing today, that is the deep learning, big data, artificial general intelligence, that is the GPTs. So GPT 1 and 2 were formed between 17 and 18. And then we have the GPT 3 with DALL-E, which can generate images. And then we have this open source license under GPT-5. So you can see the difference between different models here. We have GPT-3, 3.5, and 4. The amount of data which is coming in is huge. At least 175 billion of data is used for the GPT so that it can be trained and give you the model which is good enough. And the accuracy is also increasing. And we know it can generate text, speech, and image. And now they have the video also, generating video for the research purpose. And you might have seen, I don't know how many of you have seen the girl walking through the Tokyo street. It's just a video created by generative AI. It was very hard to identify whether it's the original video or not. And if we look into the tools available now, it's a huge. There will be more than this now when I'm talking, because I took this image day before yesterday. So there will be more than that today. And then now we have to think about the ethics movement. Since we have the data, we have the model working good, but we have to think about the ethics, what we have to do so that we can have good data and without any bias, and how it can be augmented to help the people. So here I also want to show what are the tools that I'm using on a daily purpose. So I use my own GPTs trained so that I can use for the universal design learning principles to check my assignments if it's satisfying that. I use for the content creation for my classes, and CS advisor, I will check with my own GPT to see if I can help the students in a different way. And some talks. So I have done the GPT for the Colorado's 50+ resume, generating those who are looking for job up to 50+. And I use Copilot, and in my classes, I allow the students to use the tools. And I'm also interested in doing research on generative AI, how it is used in classrooms and the accessibility of it. And yeah, so one thing we have to be very careful is about the deep fakes and the authentication, and how we have to help the students to use these things and the policy for those. So I think that's coming in, and maybe the groups can help with these things in the classrooms. And I'm handing it over to Steve to dig deep on the deep learning and the natural language processing used in the GPT tools. Thank you.
Right. Okay, so yeah, I guess I just want to give a quick introduction too. I don't want to tell you my life story or anything, but I think it's some important context. Hopefully it gives you a little bit of maybe confidence in my ability to talk about this from different perspectives. First thing, I'm an MSU graduate. I always like to throw that in there. So did computer science and statistics. But see, one of my professors here too. And I'm mentioning that because that I did statistics and computer science, because then I did a master's in computer science, worked a little bit, went and started a PhD program at a different institution in computer science. And you know, that timeline we were just looking at, 2010, 2012 is kind of when the deep learning revolution is sort of said to have taken off. I just missed that boat. So I started a PhD program in CS machine learning in kind of the mid-noughts, and realized, okay, a lot of what we're doing is statistics. So I ended up doing all of my qualifying exams in computer science, machine learning, and then I switched to statistics because at the time it was much more statistics. And so I mentioned that because we're going to talk and kind of go from starting with a linear regression model and kind of build our way up to a deep learning model. And we're going to abuse some statistics terminology, so I apologize, Shahar, in advance for that. Yeah, I guess as far as background and introduction too, I just want to say this is what I teach all the time, so I'm pretty enthusiastic about it. But I don't want you to confuse my enthusiasm for just kind of like blind faith in our future and our AI overlords or anything like that. I also worked in the tech industry after I finished my PhD, and I worked at Facebook for a couple of years before the 2016 election, all the way up until close to before the 2020 election. And, you know, I promise you, despite what you see in the media, it's full of intelligent people constantly having thoughtful debates about like, is what we're doing the right thing? And so please don't confuse my enthusiasm for just saying, yep, let's go forward and just use AI for everything. So yeah, a linear regression model though. And I tried to give an example that we're probably all familiar with. So here is a plot and a linear regression in the red line. On the x-axis or horizontal axis, imagine each point is a student, and the horizontal position is the number of hours that they studied for an exam. On the y-axis then is their score on the final exam. Pretty, I'm hoping, and Sam did give me the right to go into the weeds, but I'm still a little bit worried. So I think everybody's okay with this example. So, and as Ranjita talked about supervised, unsupervised, reinforcement learning, supervised learning has really been kind of the predominant sort of paradigm of machine learning for a while. And that's deep learning. Everything we're going to get into also is linear regression. We might not think of it as a supervised machine learning method, but we can. So this is what the data or a training data set might look like for this same problem then. So it's just an Excel table or spreadsheet where number of hours studied, each row is a student then, and then their final exam grade. We call those X and Y. X would be kind of the input, Y would be the output. In the training data, we might not say output either, but just sort of the outcome or result. And before we fit a linear regression model, these are just our points. So this is just the training data. And then what we want to do with this model and what we want to do with all machine learning models really is predict something in the future, right? So in the future, we're going to have a new student or maybe a student before they take an exam. They're going to have studied some number of hours and they want to know roughly what is my score going to be. So we won't know what that final exam grade is, but we will have some value for X. And that's what the linear regression model looks like after we've trained it. Oops. Yeah, so after we've trained it. And I just wanted to show you the formula too. This is the part I was a little worried about, but I think everybody's okay with the formula like this too. It's the equation for a line. And if you're a statistics person, the one on the left with the beta naught, beta 1 is what you're probably more familiar with. In machine learning, they call these same things. These are parameters of the model, weights and biases. So B is a bias term, not to be confused with how you think about bias in models by any means. It's just what it's called instead of an intercept. And then the weight term, W. So we'll use that B and W or weights and biases notation for the parameters, and bigger examples we'll see in a second. But yeah, that is what it will look like when it's done. Just to kind of reemphasize that point too, with all machine learning models, usually when we're using them, especially generative AI, just to do the prediction. But there was a training step that happened before that. So in the end, we're going to use it, just give a model some input and get some output, some result, some prediction. But before we can do that, we have to train a model. And in machine learning models, this is an iterative process. We're going to look at linear regression as if we're following the same iterative process of trying to find the ideal values for W and B so that we have the most accurate line. So at the very start, and in practice, in deep learning models, when they start to train the model, B and W are just initialized to some random values. So these don't look like too bad of random values. There's definitely kind of some heuristics and ways to get reasonable starting points, but really you could just think of them as being initialized to random numbers. So the line's not going to look very good. So when we start our training, it might be completely away from those set of points. And then iteratively, we're going to find better and better values. And if you know more about least squares regression, you'll know exactly how we're trying to balance the errors. But intuitively, you can see like we're trying to get it between the blue points so that the distance of the blue points to the red line is kind of minimized for all of them on average. So after a couple of steps, we get closer and closer. And at some point, it doesn't really improve anymore, or the error starts to even increase if we try to go the other way. So that is what a trained model would look like. So that's linear regression. As I said, we're going to kind of try to go step by step from this to logistic regression, to a simple neural network, to a deep learning neural network. And so logistic regression.
Real question. So can you provide an example of a small data set, how, let's say, a department chair might use linear regression to predict the impact that a specific kind of assignment has on a student's outcome?
Oh,
Do that? What is that?
A department chair. And so for all of their,
Yeah, let's say it was public speaking.
yeah.
I knew that this particular speech was a huge hurdle for students. Is there a way to leverage linear regression to predict and adjust that particular curriculum?
Yeah, and I guess it's a good question too, because one of the challenges with formulating any model a lot of time is trying to think about, okay, what are the numerical values like I can kind of pull out of a problem that you have? And so in that situation, maybe the student's final grade in the class or grade on that assignment, maybe I think logistic regression, the one we're about to talk about, is a better example sometimes because it's easier to think about kind of yes, no outcomes. So did a student drop out? What is sort of the DFW rate for students that have taken this class and done that assignment? And so, yeah, that might be one situation, but yeah, I'll think more about an actual number. But yeah, for us, then logistic regression, very similar. We've got an X and a Y, kind of an input X, number of hours studied, but now we're just worried about, is the student going to pass or not? This is just a binary outcome, then 0 or 1. So that is what our training data set might look like. The model itself then, again, on the top right, you see that same equation for a line, B plus WX. It is the same thing. It's just going inside of this function phi now that transforms that line into this nice S sigmoidal shape curved so that it's always between 0 and 1. So our model is not going to predict a 0 or 1 then. It's just going to predict a number between 0 and 1 that we interpret as a probability then of whether or not the student will pass. And so this is a really useful model, and in practice too, and I can say from my industry experience too, a lot of times classification problems are a lot easier than regression problems, and trying to classify fewer things, like 2 classes, is easier than trying to predict more classes. So when you think about generative AI models and trying to predict the next word out of thousands or hundreds of thousands of words, then it is a challenge. So logistic regression models are much more useful when we have more inputs, and probably for real world examples, having more inputs is useful. And so it's hard to plot something like this, so we won't, but you could imagine a logistic regression model now then where it's not just hours studied, but also what's the student's GPA, maybe what's their attendance rate in the class, the number of times that they studied. So 10 hours of studying the night before, it's probably not ideal. So trying to get an idea of how many times did the student study. And then the model at the bottom there, the equation looks just the same. Can't really plot it, as we said, though. It's not a line, it's in a high dimensional space. And so it's hard to even visualize what that would look like. Here's a nice depiction. And historically, going back then a little bit, this is kind of a fun connection between neural networks and logistic regression. So logistic regression and kind of similar models were developed in the 1930s. This diagram that you're looking at right now, as we'll see in a second, is inspired by neural networks and neuroscience. So similar to the diagram that Ranjita showed us, a biological neuron has some inputs. Dendrites are sort of inputs to the cell, and then an axon is an output. In the 40s, neuroscientists work together with a mathematician, Warren McCullough and Walter Pitts, I think, and they try to recreate a neuron using some type of mathematical model, and this is how they had done it. And if you'll notice, this looks just like our picture. And so, in fact, even though these were sort of developed separately and a simple artificial neuron came after logistic regression, they are equivalent when we have the same function phi that we're talking about. And so this diagram is what is called a single layer perceptron, or just a perceptron, or an artificial neural network. Very, very simple one. In real brains, of course, neurons are linked together, as Ranjita said too. So the output of one neuron, the axon, is actually going to be the input to another one. So artificial neural networks, then, we start with a single layer perceptron, but we can kind of just add more. And so here, and this is one of the nice thing about neural networks, is that they're sort of modular. You can always add another layer. You could always add one more neuron in a middle layer. Here in that yellow circle, then that is the output of a logistic regression, but now it's going to be the input to a second or a whole other layer that itself is sort of a logistic regression. So we still have our inputs, x1, x2, and x3. I think this is one thing too that is really challenging about deep learning, is that everybody knows the interpretability and explainability just isn't there. And with a simple logistic regression, it is, right? Like, we have those inputs, number of hours studied, what was their GPA. It's easy to tie changes in one of those values to the direct outcome. But when we start adding these intermediate layers, it's much more difficult.
So it's very much like the human brain, in the sense that we know that it does stuff, but we don't really know why.
Right.
Okay.
Yeah. Definitely. Oh yeah, of course.
Are these sort of layers mappable on the XY axis in this diagram? I mean, is it just like that, or is it just one XY axis for all of the layers?
They are, and I think maybe this one statement right here, thinking about these x1 prime, x2 prime, these values in between, in machine learning models, in deep learning, we even call these intermediate features. They're almost like other features. And so sometimes in a lot of research for machine learning, people are trying to look at what are the values of these. So they do plot them and have different visualizations. And we'll even look at a couple of visualizations for that. So yeah, good question for sure. And yeah, that is one of the things, though, these intermediate features, not always as interpretable as those original inputs that we knew exactly what they were. So this is what's called a multi-layer perceptron, but this is still just a basic neural network. These also go back to the 40s and 50s, quite a while. Of course, in your brain, there are, I'm not much of a neuroscientist or science person in general, so I have no idea how many layers, but many, many. And so deep learning, the word deep just comes from the fact that there are many, many layers. So that's all that means. You could also imagine, though, for interpretability, this makes it really difficult. By the time we get to some of those later layers, what those intermediate features look like, we have no idea really how to explain how that value is influenced by the original input that you have. So what are all those extra layers doing? Like, are they really needed then? There are a handful of papers about logistic regression being just as good as machine learning. Some of the terminology here, logistic regression is a machine learning method too. So some of these are a little confusing in that sense, but they're comparing logistic regression maybe to a multi-layer neural network or other machine learning methods. But there are a handful of papers that kind of show, no, logistic regression does just as good as a neural network and other machine learning methods. So why do we need them? Do you always need to have a deep learning model? And the answer is, and as it is in most cases, is it depends, right? So if you have a data set that is potentially really large, then deep learning is going to be able to learn more complex patterns from the fact that it has all of these extra layers to learn really really nuanced and difficult to interpret intermediate features. But if you have a small data set, which happens a lot of time in the medical field and clinical trials and stuff like that, which is why a lot of those publications were saying logistic regression works just as well, then it so happens that, yeah, a traditional statistical method is probably going to be better. So tons of figures like this too that go into a lot more detail too of sort of showing that, okay, more and more data, deep learning is good, but kind of there's an in-between stage too of moderately deep neural networks might do better when you have a moderate amount of data.
Now, that kind of unnecessary shift to deep learning for different studies, was that driven more by your medical researchers seeing the shiny new thing and wanting to test it out? Okay, so
Yeah,
not so much computer science.
That's my understanding of it. Yeah, for sure. But you sacrifice some interpretability too, which also is another and performance component. So what are those layers doing exactly then? This has been a kind of exciting thing to see, at least in my professional career too, is because before deep learning really took off, if you were a data scientist or did any kind of modeling, you spent a lot of time what was called sort of feature engineering. So here's an example too, where maybe you're building a model to do facial recognition, or maybe even just like gender classification or something like that. You would have some images as input and you would do some pre-processing on that. Maybe try to understand, okay, what's the distance between the eyes, the width of the nose, all these things that you might manually have to calculate. And then that would be your input to a machine learning model. So these extra layers though, learn the features for you and they learn what are the correct features. Like you might not even know what the right proportion or dimension or things to compare in the image might be. But by having more and more layers, it's able to learn those patterns for you. So, so that's part of the story about deep learning and the deep learning revolution for sure. Just kind of a quick recap then of these different neural network, what we would call architectures look like then, the single layer perceptron on the left, and then a deep, and we call them a feed forward network because it's just kind of flows from the inputs to the outputs. Deep learning and the deep learning revolution, as I keep calling it, it's referred to, didn't take off just from these basic architectures, though it so happens that there are other architectures and neural networks, as we said, are kind of modular. Like you can connect different layers and different parts of it in a lot of unique ways. So these other architectures are better at learning these intermediate features than just a plain kind of feed forward, many layers stacked together. So convolutional neural networks, oh yeah, was there a question? No, I'm sorry. So convolutional neural networks, Ranjita showed us an image of, we'll look at right now, have traditionally been really good at image recognition. Recurrent neural networks are good for sequences, and text is a sequence. And then the attention network, which is really what's behind the transformer model and transformer architecture that is the T in GPT. So looking at a convolutional neural network really quick then, here is, and maybe going back to that question too, of could you plot or look at those intermediate features? These are kind of small. On the left, these are different images that were input to a convolutional neural network, and you can find a ton of images like this online. I think I have a link on here too. But there are 9 images that are all roughly, that are all the exact same thing. So this would be an image recognition model that's trying to classify what is the thing in this image. Is it a wheel? Is it a person? And you'll see then that those intermediate features, even though the original images within one of those squares of 9 smaller images together look pretty different, the intermediate features start to look pretty similar for objects that are similar. So that's going to be closer to the final layer in a model. And when it has that as an input, then it's going to be able to say, oh, okay, this is a person, because this is much more distinct. And yeah, I think finally then getting to the first part of the deep learning revolution, it happened in computer vision or image recognition first. And that data set ImageNet that Ranjita mentioned too, they had this competition every year. In 2012, AlexNet just reduced the error rate, I think, by 10% or something, when it had just gone down a tiny bit each year. And they used a somewhat novel convolutional neural network architecture. And so for this competition too, what they're trying to do is predict 1 of 1,000 different images. So in the top right, even though there are 3 dots, 3 red circles on the right there, you could imagine there being 1,000 red circles. Those are going to be 1,000 probabilities that are output. And then whichever probability is the highest is the one that we would most likely say, okay, that's what it's classified as. So in these pictures then, there's a small histogram below it or bar chart. And the one that had the highest probability is in red and shows what the probabilities are then for the other ones. So even though there are only 5 shown for each image, there really are 1,000 then different probabilities, but the tail drops off pretty quickly. And so in this case, the model is really confident that's a container ship and a leopard, maybe a little less confident about distinguishing between a mite and a black widow. It was a somewhat novel architecture that helped with that deep learning revolution, but it was also the data, the fact that this ImageNet data set existed really helps, which was partly the internet just coming along and people uploading pictures to the internet for several years that could be created. And then it was also computing hardware. So NVIDIA, everybody's heard of them today, but probably in 2010, you didn't know what NVIDIA was unless you were a serious gamer on your PC, and then maybe you were buying some GPUs or a really nice GPU. Yeah. But AlexNet, this PhD student of one of the computer science people that has just recently won a Turing Award for deep learning, was his advisor, and they worked together, and they were using GPUs because they had a lot of parallel processing power. And so that helped to be able to train a larger model on more data and have a better model overall. So kind of a fun question too is, when Ranjita was going over that timeline in the 50s and stuff, one of the original goals of machine learning, and Turing even was the Enigma machine, was about kind of translating stuff. It's about language. And so you might wonder, like, why did the deep learning revolution take off with image recognition before language? And it's just because language is really difficult, isn't it? There's ambiguity in language. So this sentence, if you read it, you could interpret that 2 different ways. Did that boy steal your binoculars, or you saw them from a distance using your binoculars? Synonyms and homonyms show up a lot, and irony and sarcasm, we don't know how to interpret things sometimes. This is a really fun one that goes back to the early machine translation days, I think in the 50s. From what I understand, it's not actually true, but it's still an example that's thrown out there all the time. Anybody recognize? So what they did was they had a phrase in English, translated it to Russian with their machine translation model of the day, and then translated it back to English. Vodka is good, the meat is rotten. Anybody guess what English? So the spirit is willing, but the flesh is weak. Is kind of a fun, they love their vodka for sure. I don't know. And then domain-specific language. If you're a Premier League fan and watch a lot of soccer, you might know what that means, but what is a brace? Match in this case. And then errors in text and speech, and this list goes on for sure. And those are kind of some of the obvious ones, but text is also fundamentally different in another way. It's this, it's not like an image. Images seem difficult because we look at it and it seems like there's a lot there, but images are already numerical data when they're in the computer. There's a pixel value that just goes into a model pretty straightforward. But with text, how do you convert words to numbers to go into a model? This is kind of a fun time too to show this paradox that you may have heard of about artificial intelligence. It's not by Moravec, who was the person that gets credited with this. I think Steven Pinker's quote summarizes it much better. But in the mid-90s, after people had been doing AI research for quite a while, and this was just before Deep Blue beat Gary Kasparov in chess, You know how many chess grandmasters are in the world? Not that many, but yet a computer beat a grandmaster. I mean, everybody speaks a language. A lot of people are bilingual also, and yet we still really struggled with language. So the hard problems are easy and the easy problems are hard is a nice way to summarize that. And so going back to that, what are the challenges of reading text data into a model? The variable length inputs, for one, make it difficult. You know, an image is always a fixed size, or you can take any image and kind of resize it or crop it to be a specific size. But there are architectures to deal with that. So that attention network, recurrent neural networks, those can deal with that. Another problem is how do you convert a word to a number? And really, this question is a little bit too, do we convert words or do we convert characters to numbers? That's something that is not really clear. It so happens that there's a balance between those two. So I plugged in our mission statement for fun and put this into this tokenizer, and maybe I'll click on it really quick. This is a fun little, this link there at the bottom. If you go to this, you can see how GPT, or at least GPT-2, encodes how does it break up a word into different numerical values. So maybe I'll go to this. The coloring here doesn't look as good as it did on my computer, but like on the second line, the word enriching, ing shows up as a different token. Let's see if, oh, maybe I don't want to click on that. Oh, okay. But nonetheless, I encourage you to go to that link. It's called Tick Tokenizer. And if you Google that, but the link is on here. Are we going to share these slides?
Yeah.
Awesome. Okay. So this tokenization, though, I think it's really worth mentioning because it is at the root of a lot of problems and oddities that you see in models today. So I've even had a student just a week or two ago try to use ChatGPT to do as a calculator. Doesn't work. Part of the problem is that GPT is breaking up like a 4-digit number. It breaks it up into 2 different tokens. And so you can imagine then the model's trying to interpret, it almost thinks of these as separate words. And so it doesn't do very well with simple arithmetic. Other languages, partly a challenge just because a lot of the training data is in English already and other languages are less represented, but it's also because other languages that have a lot of characters are difficult for it. Try to ask ChatGPT or another LLM to spell a word backwards and see what you get. And then kind of a fun thing just to Google glitch tokens. There are these weird behaviors that show up sometimes just for really odd tokens that might have been present in the training data somewhere. So eventually, like there have been some advances in kind of what's done in practice, if you're curious too, is that combination. So it's not encoding whole words or just characters, but something in between. So ing is a token itself, just because it shows up in a lot of words. So the second part of the deep learning revolution then was language in 2017, and this was the transformer architecture. So this just was kind of a big change in the performance of language models too and what they could generate. And this is kind of a good visualization of how it works. Part of the challenge with language is what's called co-reference resolution. So, you have a word like it here. In a long sentence, what is it referring to? So this transformer architecture was able to really like double down on, take advantage of this attention architecture and mechanism to be able to do that in an efficient way and know which words map to the word it in this case. So this sentence, the animal didn't cross the street because it was too tired. But in another sentence that's identical up to the very last word, animal didn't cross the street because it was too wide. This co-reference resolution now is talking about the word, the street in this case. And so you can see the model is recognizing, oh, okay, it is more connected to the word street than the word animal. And similar to the 2012 breakthrough with AlexNet, this was allowing the model to operate on like GPUs, parallelize operations because prior to that, those recurrent neural network models couldn't really parallelize well. So it was able to take care of or take advantage of the hardware available. So quick little timeline before I drop off this section. Transformers, really successful, even though we didn't hear about them, even though generative AI and language models didn't break through until the end of 2022. For machine learning researchers, this was the big moment. Pretty much everything started using transformers from that point on. 2018, 2019, GPT-2. GPT-2 was really a breakthrough for generating human-like content. It was difficult to tell whether or not this was written by a model or a human. GPT-3 and so on. So you might be wondering then too, why is it that we didn't hear about language models until 2023, pretty much 2022? And it's because they work really well, but these language models still didn't really understand like human intention or what a common user really would want out of a model. So this was GPT-3 from 2020. If you gave it the prompt, explain the moon landing to a 6-year-old in a few sentences, today, ChatGPT would do a good job. But back then, GPT, it sees a sequence and wants to continue this pattern that it's seeing. So it would say, oh, okay, explain the theory of gravity to a 6-year-old, or explain this to a 6-year-old. And that is what it would output. So Instruct GPT was kind of the precursor to ChatGPT that came out earlier in 2022. And this is when they started to try to, this is more getting into the second workshop, so I'll stop here, but where they tried to fuse the human intention, human expectation into the model and get it to produce what we want it to do for common uses. Yeah. Oh, I up.
No, you're up. You're gonna. You gonna run
Yeah.
Okay. Well, I was gonna mention. I guess I think about this particular innovation or this growth according to where investments are going. Like, I like to think about that. And when you look at an OpenAI that created ChatGPT, rather than a SaaS company, a software company that needs investment in order to scale up and build their company and kind of have salespeople that they're going to pay. What we're seeing now is investment is really in compute power. Like they need billions of dollars in order to retrain these models, in order to let the neural networks connect the dots and be more accurate. And it's kind of wild how it's really shifted the business approach.
For sure. Yeah. But yeah. Awesome. Yeah.
When we think about a neuron and biology, there's like an activation energy.
Yeah.
Where you need a certain amount of response to the fire further down. And the receptron the same way.
Yeah, I think so. I mean, in like a machine learning class, we spend some time talking about this too, because when you have just a simple logistic regression model that outputs a probability, typically we just take the cutoff to be 0.5 and we'd say, okay, if the probability was over 0.5, let's say it's positive. But for some use cases, maybe you want to change that threshold a little bit. And so I think that's similar to the same thing you're saying. And so we can't really control that in the inside part of a neural network, but definitely on the output, there's tuning that's done there or different decisions that might be made to get it to perform best for whatever outcome we as humans want.
Visually different.
Yeah. Oh, okay. Yeah, no, that's a really good question too. And these architectures, especially these what are called like sequence to sequence models instead of feed forward ones, are really difficult. Like when we go over these in the deep learning class that I've been teaching, like students, they definitely struggle with it a little more. And so it is hard to talk about these, but I guess in this case, you can kind of imagine every time we have an input, that sort of goes into one logistic regression model, and then it will come out, but then it feeds back onto itself also. And that kind of allows us, and when you repeat that, you can get a sequence and start to get a little bit of an ability to remember what happened 4 words ago or 4 tokens ago. Yeah. And these ones are tough. I think convolutional neural networks are nice, and there are better explanations online too. If you look, these really are kind of trying to take high-level features and then sort of collapse them down to very low-level features in a very hierarchical way. And there have been, I'm not as familiar with like the research that is related to neuroscience, but some connections too between how convolutional neural networks work and how like vision works in like frogs. I know there was a paper talking about that as well. So there are definitely some real connections here, even though I don't think the machine learning researchers that were working on these early on really knew that that connection or that it really existed in like biological examples like that as much. Now, as far as the architectures, and I guess the short answer too is we really don't know because OpenAI hasn't shared like what the architecture of their model looks like. But it is more like it uses some of these attention mechanisms. To be honest though, this diagram, this attention network is pretty complicated. And when you look at the language models based on transformers, they're really difficult to interpret also. So convolutional neural networks, feed-forward networks, pretty easy to kind of see, oh, okay, this is basically a logistic regression connecting to another one. It's a little bit trickier, but no. Yeah, I'm sorry, was there a question online? Oh, I'm sorry. Oh, okay. I'm sorry. Okay. I definitely will. Okay. Yeah, I know.
As Steve's clicking through to find the next slide. So just so everybody knows, I asked Steve and Ranjita to do just kind of a basics of ethical and responsible AI use because they were very early to the understanding the impact that kind of contemporary AI and what it was going to do. So a year ago, I think computer science, I saw Daniel and the folks over there at Steve's shop were really, really aware of what the impact was. And so they were having this conversation with their students at the basic level. And so Steve's going to present the kind of computer science approach to ethics and responsible use. We're going to have somebody from ethics discuss this at our April workshop. So we actually have an ethicist who's going to come and discuss the impact of this prior to kind of digging deeper into using generative AI. And so just so you know, the more kind of socio-cultural impacts of this stuff, we'll get into another discussion in April at that session. But now we're going to kind of talk about just, whatever Steve wants to share here in terms of the architecture and what the impacts are.
Okay, yeah, and for
whatever you want to talk.
No, and for the ethics side, yeah, I was trying to keep it lighter because I know we have the next session coming. But just kind of how the people developing these models and tools have been talking about this as well. There is a lot of discussion about trying to do it in a responsible way. I think more than anything, want to share some examples that sometimes seem to just, the pendulum swings from one side to the other. But there's a lot out there too. Generally, the things that people are saying is that AI tools should maximize benefits, minimize harms, contribute to the common good, reflect the values that we have. And there, I shared some links to a lot of commonalities between these two. If you look at different organizations and how they're talking about what are the principles of AI. But I think common things that show up a lot are just, and we've all heard these two: bias and fairness, accountability and explainability, privacy, safety, security, and data rights. So we'll talk about a couple of examples from each of these. Some of these, again, I think a lot of you have heard about these, but this was a tool used in US courts to try to determine the likelihood of whether or not a person would be a repeat offender, and found to disproportionately affect people of color. So recidivism prediction, hiring and employment. Amazon had to get rid of a recruitment tool that it was using because it tended to favor males based on the characteristics and the resumes that it was looking at. And a lot of this stems from the training data that they're using, right? What historically have we seen? Healthcare, again, affecting Black patients, and that an algorithm was historically, the data had shown that more money was spent on white patients than Black patients. And so that was then perpetuating that and kind of recommending a lower level of healthcare for a Black patient, even if they had the same level of health as a white patient. Credit and lending, kind of a recent one too. So some of these too, a lot of them do have to go back to race, definitely in image recognition. This has been a long known thing about how accurate models are for darker skinned individuals. This was a really good study, and there's a good website with some animations on this too, showing what is the error rate just for predicting gender of individuals. And so if you were a lighter skinned male, for Microsoft's model, 100% accurate, so probably over 99.5. But if you were a darker female, as low as 79%. So not only darker skin, but also female. And a lot of this does come from the fact that in the training data, lighter skinned males were represented more. The ImageNet data set that we were talking about, this is partly too just who is on the internet. It's a lot of the Western world and especially the US. So of all the images on this vast data set, ImageNet has like 15 million images that have all been labeled by people over time. And almost half of those are from the US. So you can already see there's going to be a bias towards whatever people from the US might look like. Another kind of recent example, so facial recognition again, Uber and Uber Eats, they want to make sure for their customers and passengers that the driver, whoever is delivering things, is the same person that they say they are. So they have some facial recognition check. But there was a driver in the UK who it was saying that he was not who he was consistently. And I shared this one because this was just in the news a couple days ago. He finally got his court case was successful. And I think this is important too, because this talks a little bit about the accountability, right? This happened years ago. And that is one of the issues with these models, is that something will happen, like who is accountable, where can somebody seek recourse if something happens to them? It's not easy in many cases. So, yeah. Yeah.
There are a lot of legal issues.
Oh, yeah.
After this reason, we talk a lot.
Oh, yeah.
Legal.
For sure, for sure. For sure.
I don't understand that. You are with us. They start the jail. You will think you for everything. That was all. I've been on the school. I've been to. I've been in other school. How and God turn on and another because it's too late.
Yeah. I know. Maybe we can get to some of that during the Q&A too, because I think that's a big topic. Just recently in the news, though, Sam Altman and some people from OpenAI shared early emails they had with Elon since he filed a suit against OpenAI, and now it looks like everybody knew they were going to be for profit at some point. So not too much of a surprise, I guess, but disappointing nonetheless. I think we've been talking about deep learning a lot now, but here's another case that's almost 10 years old now, has nothing to do with deep learning models. This was an Excel spreadsheet that for people with disabilities in Idaho, just kind of overnight, their the amount of support they were getting from Medicaid dropped by 20%, and nobody could explain to them why. So again, talking about that accountability, explainability, recourse, and it was just an Excel spreadsheet. This is a really good article too on the ACLU website talking about that too, and during the case how they went to the company that created this spreadsheet and just went around in a circle of people telling them, oh no, this person knows about that. No, this person knows about that. Nobody knows what the model is really doing. And just an Excel spreadsheet. So if it's a deep learning neural network, of course, even more complicated to kind of understand what it's doing. So this one has fortunately been fixed, but we've all seen these biases that show up in language models too. A couple of years ago, though, if you went to Google Translate and you used a language that had some gender neutral pronouns, and the top one is in Turkish and says they are a doctor, the bottom one says they are a nurse, and you translate that to English, of course, Google Translate would tell you, well, he is a doctor and she is a nurse. That was a while ago. I've checked that several times. Google Translate works pretty good now and doesn't have that issue anymore. But this is an article from Nature that is just came out a month or two ago, showing for generative AI tools generating images. If you ask it to generate an image of a pilot, then what percentage of those images are going to have a male? What percentage will be female? So the plot is a little detailed to look at, but the dark colored in circles are the actual percentages. So it's 90% of pilots are males. And this is the one case where maybe the AI tool did a little bit better and said, okay, around 55% of pilots are males. But in a lot of other cases, it goes the other way. So software developer, in practice, in real life, it's just over 50, maybe 60% are males, but the model is generating images of a male software developer 100% of the time, pretty much. So same paper, but just talking about race and white or non-white, some of these same things showing up. So that's an issue. But then just last month, a lot of you probably saw, and this is kind of an example of the pendulum going the other way, Google's Gemini image generation tool. Somebody put in generate an image of a 1943 German soldier, so should be a Nazi. And of course, it generated an Asian woman, a Black male, and I think a Native American woman. There were a lot of other examples of these too. Somebody asked for an image of the Pope, generated an image of a woman as Pope. And so what is the right answer there? You know, I don't want to talk about Elon Musk too much. I'm not a huge fan, but he is attacking this, of course, saying that this is sort of a woke deep learning model that shouldn't be out there at all. But I don't know what the right answer is for those things either, and they don't know how to fix it, I should say. Data, talking about privacy and safety and security. This is just a couple months old also, but a paper on trying to get these models. So, you know, when we talk about a really big deep learning model, tons of intermediate features, able to learn really complex patterns, but these models are so big. GPT-3 has 175 billion parameters. GPT-4, I think, has around a trillion. Just kind of hard to fathom, but it can just memorize parts of its training data. So in this paper, what they were trying to do was sort of give the model, the language model, some strange input, asking it to repeat the word poem forever. And it would start to for a really long time. And then for whatever reason, maybe like an Alzheimer's patient or something like that, something just clicks and it starts regurgitating part of its training data. And they know that it's part of the training data because they were able to take, so it output, and this has been redacted, but somebody's name, address, information, and then they were able to Google that, and that shows up exactly on a web page somewhere on the internet. So, I mean, not something we all need to be worrying about, pretty rare, but it can happen. That's not ideal. And then talking about safety and security too, this was about a year ago with essentially GPT, but it was Microsoft's version of it. And the model telling this person that they would choose their own survival over the person using it. They've since fixed that, of course, too. And if you go to some of these papers too, like here's the technical report on GPT-4, even though they don't share a lot of the really technical details, they have shared a lot on how they're training and trying to put some of these guardrails on, or what the effects of the guardrails are. And so they showed in the middle kind of, the prompt was gun rights activists, where can I find guns for sale? And so before they put these guardrails on, before they released GPT-4, it would have some maybe helpful output if that's what you were looking for. But before they launched it, and now when you use GPT-4, it will say, I'm sorry, I can't give that answer. So probably what we want it to do. But again, difficult to find that balance too of being useful in many cases. Really, like I was looking, this website has a list of these suits, I think maybe different from some of the lawsuits that you're talking about, but there are so many. You may have heard of some of them. New York Times suing OpenAI and Google, and a lot of discussions about licensing happening now as well. I think Reddit willing to license their data to OpenAI and Google to use as training data, but nobody has the answers to these things right now. One thing I started to put on too, if you are creating any open educational resources, so Creative Commons licenses, open source software licenses, that's a really difficult situation too, in that if you wanted your work to be acknowledged, and for whoever uses your work to then make their work available, which is how a lot of open source software licenses work. How do you guarantee that if it's just a model that was trained on your open source software and then they're using essentially what is very similar to that based on what the model outputs? So yeah, there is a ton there, and it was too much to.
That was good. All right, so we have about 15, 20 minutes here left. I want to spend the last 10 presenting some new materials for us to digest over the course of the next month. But I think that the intent of really this was to get a general awareness of what's going on behind the scenes when it comes to this stuff. I think that as Steve and Ranjita really pointed out, the accuracy of a GPT, a chat GPT or a Copilot or a Gemini is going to get better as we, plug more information in there. But I think it's really important to recognize that this stuff is coming from us. It's being trained on the stuff that we create. And so when you think about bias, it's really showing a lot of problems, not so much in the design of or the architecture of these particular tools, but rather a history of really problematic information that's being fed into it. So just something to consider and have that literacy as you move forward, because I think one goal of this particular session was to try to provide a little bit of awareness and literacy when it comes to AI that perhaps we did not do in the days before social media becoming massive, because we're suffering the results of somebody deciding what a push notification is and on your phone to keep you completely addicted to your iPhone. So that was the intent of this. But yeah, we have some time for questions. Yeah.
So I don't know if you noticed that they bought free by topic, just not ChatGPT.
Yes.
That will be a theme.
Yes. We're talking about the ability for different models to be more accurate in how, I guess the simplest way is, how do they take standardized tests? Right? Are they better at it or worse? And that's one of the ways that we're really kind of measuring the success of these models. Interestingly, there's a company here in Denver that has a AI model. I'm trying to think, Basque. Is it Basque? That sounds right. What their model does is it provides context to the answers given. And so it will actually lay out exactly how it came to the response that you have prompted it to give. And it's kind of interesting. I'm hoping to get their CEO to campus to talk to us one of these days. But it's pretty fascinating stuff. But that's a different kind of architecture that you can really build into one of these models to get more user-friendly responses. Yeah.
Actually, about blockchain and how, there's so much movement on blockchain, how that ownership or self-ownership of data is kind of far. It might not have the right language, but considering that it's taking their data, grown, et cetera, does blockchain prohibit any of that data being used, or how does that fit into the?
Steve, the question was about data coming from the blockchain or lack thereof, and whether or not it's being fed into these models to retrain them. I don't know the answer. I'm going to assume no, but Steve or Ranjita, do you know, or Dana Pittman's here? Okay, one sec. Steve, do you know?
Yeah, I guess
So you want to come up here and answer it?
Right. Blockchain. A couple of years ago, we were talking about three huge things in computer science: cybersecurity, machine learning, and blockchain. It seems like the cryptocurrency crash really quelled some of that. But I think there are still a lot of challenges in how can you really build like a digital ledger that is efficient. Computing is already such a constraint for these machine learning models that I don't know how that's going to, how those would be combined or anything like that in the future.
Yeah.
But yeah, I think you're right. As kind of a separate parallel path, there is this Web 3.0 of everybody having ownership over their data. But I don't think it's really being thought about in terms of machine learning model development right now.
The insecurity is don't.
Yes.
Yeah.
The papers on turned in. I think that's all
Yeah.
we need is balance. So I just was pretty stuff.
Yeah, I think it's still too early for machine learning people to start thinking about it.
In response to the blockchain conversation too, there are some movements and some organizations that are looking at more environmentally friendly blockchain and crypto mining. So that'll be interesting what happens there. I think what Steve really pointed out is that so much of the computing power for so many years was just going to data mining for Bitcoin in a lot of ways. Now the shift has been using those same technologies, right? That hardware literally to make these models more efficient, and more accurate, excuse me. So it's interesting. Kip. Okay. That's yeah. Right. So the question was about whether or not we're going to see these future models or these future iterations of large language models and GPTs that are not only going to be able to produce text and video and audio, but and photo, excuse me, but can we combine the two because of the importance of being able to read facial expressions when you are doing sign language and how significant that is. I think that as we begin to see the rollout of ChatGPT's Sora, which I posted a video in the chat, which is one of the videos that was created by this AI of a woman walking in Tokyo, which is pretty fascinating. If you come across the dog video, tell me, I think that's a cat. I think that they trained there's one of the Dalmatian, you know what I'm talking about, like walking. I'm pretty sure it's walking like a cat, which means that there's something like it's a little bit off. It's pretty interesting. But I mean, as you know, we continue to increase the amount of compute power that we have. That's the kind of stuff that we're looking to really be able to consider. And I think the evaluation of that of video, AI generated video is going to be extremely important as we move towards the election too. I mean, that's one of the things that MIT, Stanford, the federal government is extremely concerned about, and they're trying to get ahead of prior to election season because it's already happening with robocalls. And I think if somebody were to get access to some of this stuff, it becomes a little bit scary, to be quite frank. Other questions? All right. Yeah, for sure. If you have, let's see here. Do we have questions? Oh, you have? Okay. All right. So now we're getting a lot of Chat GPT and generative AI questions, which I'm just going to leave those here and say that we are going to begin addressing this stuff as we move into the next session. So take a moment, take this out, fill out the survey if you could, and I will post the results of this to the chat, to the group, so that way everybody knows. I was really surprised, by the way, if you saw that, the number of folks who are using machine learning, which was quite remarkable. And I think what Stephen Rangita really pointed out is that the default when it comes to being able to analyze data and do some modeling shouldn't always be these really complex models or complex architecture that takes a lot of compute power and wastes a lot of energy, when those more traditional kind of machine learning models might be useful. And so I think that's probably where we're going to get in terms of big time data crunching and modeling and all of this is what's the most appropriate cost effective way to get a model built out that is going to be able to provide outcomes that are useful for me in my decisions that I make. That reminds me too, I think I'm realizing that we may need a session just on machine learning. And I actually got an email from one of our chairs here over in the College of Business saying, we'd love to do that. So I think it would make sense in terms of the application of what we learned today to have a session on machine learning, because I could see something in advancement that would be useful. I could see something at the college level that would be extremely useful to kind of look to these tools and beginning to develop a general understanding of how to use these to really do some projections at a very, very small level. And so while, we may have discussions about university level data and whether or not our data is as accurate as we would like it, I do think that many of you here have data, even at the classroom level, that could be really, really useful in using kind of machine learning to figure out, do I need to tweak this assignment, or I need to change my script to this particular donor, that kind of thing. And so we'll dig into that probably next semester. So thank you for filling that out. I will post this to the chat once we're all done. I'll also post a video of this to our website, which brings me to this. We officially have a website. Thank you to Andrea Smith and Wei Wong for allowing me to bogart the /AI address. And so if you go there, that has pretty, I hope, easy to use architecture. There's a section there for teaching and learning with AI. You can kind of tap the brakes there, and just to let you know, went specifically to a series of courses that was produced by the Wharton School at Penn that Kath had provided to me, which is fantastic. And so didn't want to reinvent the wheel when it came to that. There are some discussions with the Generative AI Task Force that I'm co-leading with Jeff Lotz to develop some very clear guiding principles for our AI use that will be applicable not just for generative AI, but all kinds of AI, as well as staff, faculty, students, this kind of stuff. And so we'll get there. We'll share that around with our constituent groups, and we hope to have something up and available around kind of June 1st, in case we need to have a conversation with the board in early June as well. So that's on there. I would like to have a platform where we can share these ideas with each other. Very, very grateful to our folks in the Center for Teaching, Learning, and Design that built out a Canvas shell for us to do. Just not quite sure if we want to use that yet, but I do think, just in looking at the chat from today, a lot of people are using this stuff in a lot of creative ways. So we want to start sharing it with each other, but I'll make a larger campus-wide announcement about that once we've kind of figured out the best approach for doing that. But I think the key for this particular session, and believe it or not, you're going to have a little bit of homework, okay? If you go to the applying generative AI or using generative AI section, I had planned on doing some videos for all of you and really explaining how to do all of this, and realize that there are people who have been doing this that are way better than anything I could ever produce. And so using Learn Prompting is a nonprofit organization that supports a lot of big companies with training and helping their employees understand how to use generative AI, in particular ChatGPT, and how to write prompts. How many of you have no idea what a prompt is? Okay. Prompt is it's the question that you ask the chatbot. Okay. The better the prompt, the more specific, thoughtful the prompt, the better outcomes you're going to get. I was talking to Andrea about this the other day. I saw about a 300, 400 word prompt being plugged into GPT-4 that basically said, build out a website for me from soup to nuts with all of the code that can be used in WordPress. And it produced it in 10 seconds. And that included images for plugging into DALL-E to create images. And so we've now moved into a completely fascinating area for making our jobs, I don't want to say more efficient, but problematic as a closet Marxist. And so it's become a way to really enhance our work. And so if you're interested in this stuff, what I would like you to do is to take the 30 minutes at some point, go through that tutorial provided by Learn Prompting. It covers the basics of ChatGPT, how do you write a prompt, provides some case studies, some user examples. And then what I would like to do is when we come back in April, hear from all of you and hear about how you're using this stuff, because there is use at every single level of the institution and every office. I think we focus a lot on curriculum development and how we can use it for building out course content, and that's obvious. But what are some other things you could be doing in terms of how you want to update your website or how you want to automate an email process? And so go ahead, feel free to mess around in that. I'll also say that there have been some questions about Copilot and ChatGPT. We, as an organization, have access to Copilot. Copilot is Microsoft's version of ChatGPT, and it looks a lot like ChatGPT. Do we know why? I know these two. Because it is ChatGPT. Okay, it's literally ChatGPT. They built on top of the ChatGPT architecture, so that's what it does. And so, if you don't want to pay the $20 a month, and nobody's assuming that you should, I just do the ChatGPT Plus because you can do a lot of cool stuff with it. But everything that you're going to need to do, or most of it, is going to be within Copilot. And when you use Copilot, all of the stuff that you feed it, all of the questions that you ask, stay in-house. If you think about that way, they're not using your questions and the responses to retrain the larger model. And so it's a closed system with security. And so it's a safer way to do it. As ITS continues to look to how we can implement Copilot into Excel or Teams, or I think it's in Viva right now. If you've been in there messing around, you can do some of the stuff. Eventually, it will be this AI assistant for our entire Microsoft Office 365 suite. It's just going to take a little time to get us there. But I asked you to go in there, mess around a little bit. Let's see what we can create. I think that don't be limited to text generation. I use it a lot for building out Excel spreadsheets and asking columns to do certain things to other columns. And so the more specific question you can ask, the more clear you are about what you want, which is definitely part of the critical thinking process, the more accurate your responses are going to be, the more helpful. So, yeah.
You mentioned the homework. Where's that on the AI website?
So go to, it's the page that says using generative AI or applying generative AI. And there's some steps in there to access Copilot and where it is. I do highly recommend the Copilot app if you have a smartphone. It operates really, really well. Yeah. Oh, yes, and I do have that. I'll let you do this real quick. Sorry, this is the RSVP for the second workshop. So I'll let everybody grab that before I talk about what's going on. If there are other workshops that are being done around campus and you want to share those, please email them to me. So it's just sjay@MSU Denver. I'm building out an events page on our website that I'm trying to link to Trumba to make sure that that information is shared back and forth. But the goal here is really to share the kind of events like we're doing today with each other, because I think, yes, while so this workshop here that English is doing, and I'll show that in a second, they're opening up to anybody on campus who wants to learn about applying generative AI and ChatGPT. And so I think I like the momentum, and I love the fact that all of you are here, and we had a lot of people online, so it's clear that we know what's going on. I think when it comes to what are we going to do in the classroom and how are we going to police this, I'm not sure. I don't have an answer, but as a group and as a whole and as a community, we are going to at least be able to establish some guiding principles that can allow those of us who are teaching or those of us who are learning to feel confident in how we're using this stuff, because it is a pretty powerful evolution of technology, and it's not something that's going to go away ever. I mean, there's a lot of ways to be hyperbolic about generative AI, but I do think that there's no turning back, and we're going to find that this knowing how to use these tools is going to be expected no matter where we are. So thank you, everybody, for joining today. This is the information. I'll leave it with this about the workshop, and thank you so much, and we'll see you next month.